Hello and welcome to Lecture 12. This week we look at waves. More importantly, we're going to look at waves to understand the terms that we use to describe them, compare the properties of waves based on the material they transfer through, and examine how waves transfer energy from one material to another. As you see, the lecture is actually titled Refraction and Interference, so we'll also look at what these two terms mean when it comes to interacting waves. The remainder of our studies are going to rely heavily on an understanding of waves. Keep in mind, no matter any other distinction we make, remember that the purpose of a wave is to transfer energy from one point to another. We'll begin by investigating mechanical waves, that is to say, waves that require a medium to propagate through. Later on, we'll look at electromagnetic waves, and they can propagate through a vacuum. Some of the key terms we'll use. A wave is a disturbance or vibration that transfers energy. When we talk about mechanical waves, we're looking at waves that transfer energy only in a medium, so some material. Examples of this will be strings, waves in water, and even sound. If there is no medium to transfer through, then the wave we'll be talking about is electromagnetic. This is a wave that can transfer energy through the vacuum of space. When we talk about that disturbance or vibration, another word we'll use is oscillation. Transverse waves have oscillation that is perpendicular to the direction that they are transferring energy, while longitudinal waves are oscillations that are parallel to the direction of energy transfer. So a transverse wave, you can think of snapping a string, whereas a longitudinal wave, you could think of stretching and shrinking a slinky. When referring to waves, we typically use the same style of diagram to represent all types of waves. To understand these diagrams, let's consider some of the important parts of a wave. First, let's draw a line of equilibrium, and this will represent the resting position of any medium we're about to disturb. I'm going to add a pink line, and this pink line is our representation of the disturbance in a wave. The first thing we'll talk about is the amplitude. The amplitude is the distance from equilibrium that any of these humps in the wave diagram represent. The amplitude could be positive or negative. Now, those humps have special names. If we go above the equilibrium line, so we have a positive amplitude, we refer to that region as a peak. And when we have a negative amplitude, or we're below the equilibrium line, we refer to that as a trough. When we look at a complete transition through the whole range of positions in a wave, we call that a cycle. So this is when we go from a starting point through a peak and trough and back to that same starting point. This range of one full cycle could occupy several positions. You could see it could be a peak to peak, or it could be from equilibrium going up to the next time it meets equilibrium going up, or it could be from trough to trough. The amount of time it takes for one complete cycle is referred to as the period, and you've seen before that we represent that value as a capital T, and we measure it in seconds. Let's look at a few more details about a wave. If we take the inverse of period, this is the frequency, which can also tell us the number of cycles per second. Also, if we measure the distance of one full cycle, we can call this the wavelength. Let's bring in a demonstration of a wave as it's moving. You'll see here that we have a 1 centimeter amplitude, so the string is disturbed a centimeter above and a centimeter below the equilibrium line, and that disturbance transitions through the string. I'm going to pause here for a second so that you can see from green dot to green dot, and that's the wavelength of this wave. And we're going to let the demonstration go again, and again noticing that the shape of the wave as it moves through the string is that sinusoidal pattern where we go up and down and back up again, and we continue to repeat through the entire range of motion. When multiple waves interact, they cause interference. Interference is what we call the resulting wave when interacting waves meet. The interference pattern will depend on how the peaks and troughs from the contributing waves meet. So remember, we have a peak when we have amplitude above the equilibrium line, and we have a trough when we have amplitude below the equilibrium line. And in this case, we're going to consider two amplitudes of the same size. The first type of interference is destructive interference. So that's when opposite amplitudes meet. So a peak meets a trough. In this case, the amplitudes cancel each other out and there is less or no energy transferred to the position where they meet. And you can see here the resultant wave is a flat line at equilibrium. The other type of interference is constructive interference. And this happens when disturbances of the same amplitude meet. So in other words, a peak meets a peak or a trough meets a trough. In this situation, we're going to consider our large amplitude and a smaller amplitude meeting. And we see that the amplitudes will combine and more energy will be present at that position. So the two positive amplitudes combine to make an even larger positive amplitude, and the two negative amplitudes combine to make an even larger negative amplitude. Interference patterns don't just happen at peaks and troughs, they happen at all sorts of combinations in between. We need to keep in mind that waves transfer energy, not material. This means that the movement in a wave is the energy. The rate at which the energy moves from point to point is what we're talking about when we talk about the speed of a wave. Now, for any particular wave, its speed will be based on the properties of the material it's traveling in. So depending on the material properties, each wave will have a set speed. If we can record the frequency and the wavelength, then we can calculate the speed, knowing that the velocity of a wave is equal to its wavelength, represented with lambda, multiplied by its frequency. From here, I'm sure you can predict that, as with previous units, you're going to be asked to answer questions with various combinations of information. So given a wavelength and a frequency, find velocity. Given a velocity and a frequency, rearrange and find wavelength, and all sorts of fun activities. Earlier we mentioned that mechanical waves require a medium to transfer through, but that electromagnetic waves can transfer through the vacuum of space. The vacuum of space means there is no medium for those mechanical waves to transfer through. This is why in space nobody can hear you scream. We're going to focus now on electromagnetic waves. As you can imagine, electromagnetic waves are made up of a magnetic field and an electric field. These two fields are perpendicular to each other. So I'm going to do my best to sketch them here and show you that you have an electric field drawn in blue, oscillating vertically, and a magnetic field drawn in red, oscillating into and out of the page. Both sets of oscillations are perpendicular to each other and the direction of energy transfer. So we're going to draw the direction of energy transfer in green, and we represent that with the vector S. And we refer to this as the pointing vector. So we're using the pointing vector to represent which direction the energy transfer points in. Now, if vacuum means the absence of a medium, and the speed of our waves is always dependent on the properties of the material the wave is transferring through, how do we determine the speed of our wave? Well, all electromagnetic waves travel at the speed of light. So this is 299,792,584 meters per second in a vacuum. Sometimes we round this to 3.0 times 10 to the 8 meters per second. For all our considerations of waves in vacuum, this will be our wave speed. And now we'll go on to look at how that affects the frequency and wavelength of our electromagnetic waves. We need to extend our understanding of how electromagnetic radiation transmits energy. So electromagnetic waves transmit energy outward in all directions from its source. Any source has an amount of power available, and that will dictate the amount of energy that could arrive at some surface. So if power is emitted at all directions, and eventually will arrive at the inside surface of some sphere, let's consider the first level here in purple, then the intensity, or what we often think of as brightness, of the light at that surface will be equal to the power divided by 4 pi r squared. If we go further away from the source, and here we'll draw this as a light pink surface, the power doesn't increase. So because the radius has increased, the surface area that the light lands on increases, So the intensity, which is the power per surface area, must decrease. We can also think about the amount of energy that reaches a surface based on the orientation of the surface. The way we talk about this is the term flux. This is the amount of energy reaching a surface dependent on the orientation. Flux is represented with a Greek letter, and it is calculated using the magnitude of the Poynting vector, so that's the energy transfer, and the area vector, which is always perpendicular to the area it represents, and then the cosine of the angle between those two vectors. Remember, the cosine tries to tell us how much of these two vectors are parallel to each other. Now we're going to try to consider what this means. Think about a circle. If the Poynting vector and the area vector are parallel, then this would be the same as you being over top of a mug and looking straight down. The area looks the largest it possibly could. Now, if you skew the Poynting vector and the area vector, this would be the same as if you had a mug sitting on a table and you try and look into that mug. The opening now appears a little bit smaller, and we draw that usually representing an oval. Now consider if the Poynting vector and the area vector are perpendicular to each other. This would be like you setting a mug on a table and then lowering your head down to so that your eye level is at the top of the mug. And here you can see that you can't see into the mug at all, so I've just represented that with a straight line. The more parallel our Poynting vector and our area vector are, the more amount of energy we're able to allow to reach that surface. We began our distinction between mechanical waves and electromagnetic waves by pointing out that mechanical waves cannot transmit through a vacuum. However, electromagnetic waves can transmit through a medium. Our primary concern about the electromagnetic wave here will be about its speed in this medium. Again, the speed of the wave will be based on the properties of the material. We should note that based on those properties, the speed of the wave will be slower than the speed of light in a vacuum. The comparison of the speed of light in a vacuum and the material is called the index of refraction, and it's calculated using n is equal to the speed of light in vacuum, which is c, divided by the speed of light in a material, which is v. V will always be smaller than c in any material because it's comparing to the fastest possible speed of light, which is in a vacuum, which means n will always be greater than 1. Something you should consider here, because the speed is equal to the wavelength times the frequency. If the speed decreases, then we must have a change in the wavelength or the frequency. But it's a property of light that the frequency remains constant, at least as accurately as we can observe the frequency. Let's move on to look at some of the consequences of this change in speed. We refer to the consequence of the change in speed of an electromagnetic wave in a medium as refraction. With this change in speed, we will also see a slight change in direction. This will occur any time an electromagnetic wave meets an interface between two different mediums. In this case, we have material 1 and material 2. The light moves through material 1, which we call the incident material, and then transitions into material 2, the refraction material. We can see that as it transitions into material 2, it will bend and change direction. So this entire range is the option for how it bends. We describe the amount of bend using Snell's law, which states that the index of refraction multiplied by the sine of the angle of incidence must be equal to the index of refraction in the refraction material multiplied by the sine of the angle of refraction. It's very important to note here that theta is measured to the line normal to the interface. So you can see in the diagram, we have our angle of incidence and our angle of refraction, and they're both measured to that vertical line that's perpendicular to the interface. It's been a while since we've had to think about this question. Based on the diagram that I just drew, and what you can see from Snell's law, is the index of refraction in the incidence material or the refraction material the greater? All right, I'll give you some of the solution here. Consider the sines of the angle of incidence compared to the angle of refraction. We know that these will be greater than 1, which means if we've rearranged Snell's law, we know that the index of refraction compared to the index of refraction on the incidence material must also be greater than 1. Thus, the index of refraction in the refraction material is greater, and C would be slower in the refraction material. Refraction isn't the only behavior of light at an interface. So let's bring back our drawing from the previous slide and note that some of the light will stay in the incidence material, and this is considered reflection. So we'll have our incidence light with an angle of incidence. Some of that light will refract into the second material with its angle of refraction, but some of that light also reflects back into the incident material with an angle of reflection. Refraction, the behavior we already talked about, is the light in the new material. Reflection is the light that remains in the same material. Some of the properties of reflection include that the angle of incidence will be equal to the angle of reflection, again measured to the normal line. A special situation can happen called total internal reflection. So when the index of refraction in the material of incidence is greater than the index of refraction in the material of refraction, it is possible for the angle of incidence to be large enough that the angle of refraction does not exist, meaning that all of the light reflects back into the incidence material. We call this angle, which is for the angle of incidence, the critical angle, and it can occur when the sine inverse of the index of refraction of the incidence material over top of the index of refraction of the refraction material multiplied by the sine of the angle of incidence, which is just Snell's law rearranged, could not be calculated. Mathematically, this happens when the bit inside the brackets is greater than 1 because we can't take the sine inverse of a value greater than 1. This is something you should be aware of for some of the problems that you'll see in the course, as it could explain why you might not be able to get to an answer for some materials. We have to consider a few more behaviors of light in a medium. Now we look at polarization. Polarization is a consideration of the axis in which the electromagnetic wave is oscillating. Polarized radiation is a collection of radiation waves that all share this axis of oscillation. Let's look at a diagram. Consider a source, and from that source we have electromagnetic waves that come with all different axes of oscillation. So we could have some waves that are vertically oscillating, some waves that are horizontally oscillating, and others that are oscillating on diagonals. Now if we consider some filter, often a polarization lens, and we organize that lens so that it is vertical, then when the source emits those same randomly arranged axes of oscillation, only the axes of oscillation that match the filter will be allowed through. The lens itself will absorb all other orientations. This is why polarized sunglasses are so helpful. It only lets certain orientations of light through, which helps protect your eyes from the intensity of the light outside. Similarly, if you have light reflecting off of water, that reflection has most of the light oriented in the same oscillating pattern, and your polarized lens will block that oscillation, allowing you to see the light that reflects off the bottom of a shallow lake, as it will be oscillating in a slightly different direction. Our last behavior is dispersion. Dispersion is similar to polarization, but it focuses on wavelength. Let's draw a diagram right away. Consider a source far away, like the sun. That source will emit light at all different wavelengths. When all of the wavelengths reach the same surface, like here, that light will appear white. But as that collection of wavelengths reaches an interface, like our atmosphere, particles in the blue wavelength are readily absorbed and then re-emitted by the particles in the atmosphere. This means that all of the blue light reflects around in the atmosphere and makes the atmosphere visible to us in that blue color. But the sunlight, now missing that blue light, shifts from white more towards a yellow. There's even more interesting things that can happen. When the sun is low on the horizon, or the source is low, then the collection of wavelengths have to travel through more atmosphere. In this case, even more wavelengths are scattered. We can see that more and more different wavelengths begin to get scattered. So above that region will appear blue, but as light transfers all the way over to us through longer and longer stretches of atmosphere, only the red wavelengths, which are not readily absorbed by the atmospheric particles, will make it to us. And this will make the sun's light and the atmosphere begin to appear more and more red. Now, we are going to require a separate branch of physics to understand why the specific quantities of energy are absorbed, but for now it's okay to just understand that dispersion is the cause of this change in color. This lecture, we explored new concepts related to waves. We introduced the distinction between mechanical waves and electromagnetic waves. Mechanical waves requiring a medium to transition through, and electromagnetic waves representing our radio waves and light and X-rays. We also examined the concepts we'll use to describe and measure waves, whether it be their wavelength, their amplitude, or their frequency. We looked at the spectrum of electromagnetic radiation, and we looked at a couple of examples working with Snell's law to determine the properties of light in different materials. You may have noticed how this lecture was really light on examples. As we finish our last few topics, the calculations are not that difficult, and thus we spend less time on showing you how to problem solve problems that are similar difficulty to previous units, and more on explaining the concepts that we're going to interact with.